Let's look at an optical dynamics example across two interfaces. So the first thing we have to do is set up the optics. While they're set up, we have an incoming ray, an outgoing ray, and an outgoing ray. Incident, reflected, transmitted. Associated with this ray or wavefront normal is the wavefront, so that wavefront normal is in the direction of the wave vector k. So we have three wave vectors, ki, kr, kt, and we know how to compute those wave vectors in terms of a normal vector in this direction. We can see it from the geometry, and same here and same here. So that's the optics part. Now the fields. We can either pick the E field or the H field in terms of how we want to set the problem up. We will look at the case where the E field is perpendicular to the plane of incidence. That means into the plane as indicated by the X. And since this is a right-handed coordinate system, the y-axis is into the plane. We know that the H field is perpendicular and that the H field and the E field and the direction of K are related by this cross product. So n hat is normal to the wavefront. The wavefront, for example, would be sitting there. And that's associated with the incident wave cross-producted with EI divided by eta, and this should be eta I here. Eta I is the intrinsic impedance of the material. So EI now is what we have to look at. If we have EI, then we can compute HI using the cross product. Let's do that. EI. First of all, it needs a direction into the blackboard or into the light board. That's the direction. Then it needs an amplitude and a phase. The phase is always e to the minus j phi. Phi I is the dot product of ki with the r vector. This is our plane. Phi I equals a constant, picks the phase, so we're sitting on either a peak or a trough, and r is equal to xi hat plus zk hat. The job then, as we'll see, is to compute the k vectors. We know the directions of the k vectors, and we then have to use this cross product to compute the magnetic field vectors. Notice that when we do this, the phase will be the same on each side, so we'll actually use this cross product to look at the amplitudes themselves. We don't have to carry around the phase factor all the time at this point. We will eventually have to write down the fields in terms of the phase factors, but it's really amplitudes that obey this cross product, because at a given point on the location of the plane, the phase is constant. We also have to look at the material properties, mu1 and epsilon 1 in medium 1, mu2 and epsilon 2, and we know what the k's are. So ki is equal to omega square root mu 1 epsilon 1, and ki and kr, this is the magnitude of ki, so actually let's write it like that. The magnitude of kr will be identical to this. We're in the upper medium. And in the lower medium, we will have that the magnitude of kt is equal to omega times the square root of mu2 epsilon 2. So what we have to do is compute the entire field. We will substitute this in. We will keep the phase factor because we will need to apply it at the boundary later on when we match the conditions. This summarizes all that we need to know in terms of the optics and the fields. Notice that the cross products are not difficult to do because eta hat, basically pointing in this direction, is a linear combination of an x unit vector and a z unit vector, and we'll do that on the next panel and then compute the values of h.